Okay. And now it's now we have to do this, right? Press here. Oh yes. Oh, so okay. Now I think I have to just put that there. Yeah.
What's can you make the division?
There is a line there, but I don't see it here.
That's not.
Oh, on the wall, I saw.
Yeah.
Now I can see that there. Zoom in a little, it was hard to read the first day. Hello, Niranjan. Are you there? So you
Hi,
are,
Doctor.
yeah, if you maybe since you use the reading, if you let us know when it is too small, that will help.
Okay.
You can also keep this here, right, at the center, because this can get longer, right? Oh. No. Next, you could try. So now this is a little skewed on one side. Okay. Okay. So I did post a. Oh, where am I posted the new homework 2. It's on the brush hour homework 1. Any questions you have? Anything in general, like, was it okay? Was it related to the class? Yes. You guys have seen this before. Like, let's say, different standard time. Name again? Nahida, yeah. Okay, here's what I'm going to do next. Nahida, yeah. And in a few days, I'll get it done. So, any comments on how the homework works? So, it can go like this. So, based on the classes, you could do sufficiently. Yeah, we tried, but I'm saying, did it feel like you were, it was sufficient? Or what can I do to make it better? Maybe that's a better question.
I feel we are possibly trace.
Trace, yes, okay, yeah. This was a problem last year also, I remember. I think there was some ways to comment. I think you were the one, right? I think it was not satisfactory how the place is going. That's all. Okay, so let's try this, okay. So the problem is, let's say we have a tensor. Notice that in the homework, I don't write those arrows because it's boldface, but it's important that you write it because otherwise it means it's a magnitude, it's a scalar. If you don't write the vectors on it, I don't think there is any way you can understand that it is a vector. So I cannot understand for sure. So I will be, those are the places I get strict. You should write a vector sign on a vector. Otherwise, I just don't know what you're doing. It seems to me that it's completely wrong kind of. Yeah. So T, let's define this as, I think in your homework it is E and B. So there are two vectors, no dot product, no cross product in between. And let me say E is equal to some E times X hat, and B is equal to E times Y hat. This is different from what you have in your homework. Notice the difference right away that if I have a vector sign, this E is not the same as this. This is the magnitude of E. Like that's what we do all the time. If it's in the same direction, then it's a magnitude. Now, so this is a geometric, whenever I write the vector signs, this is a geometric entity. This is what we mean by a vector or a tensor. Whenever I write the vector sign, it means that it has a direction. In this case, it is a tensor. It is a more complicated object than just a direction, and it is a geometric quantity. This has 9 components. These are the components now. This is not the vector itself, like we have when you have a vector A. This is the component, right? A1, E1 hat plus A2, E2 hat. Component itself has some meaning. So these are the components, T11, T22, T33. So this is AI, components. This is geometric. Like it has direction, magnitude, everything, but A1 alone doesn't have any meaning in it. It has no direction in it. A1 is the length along a certain direction. Now there are 9 directions if you want for this, and this can be arranged as T11, T12, T13, T31, T32, T33, and no, 2, right? 2-1, 2-2, 3-2, 3-1. That's the difference between these two. Same idea, but these are the components of this tensor. Now, when we say trace of T, what we mean is, so trace of T, which does not depend on in which basis we are taking the components. In this case, this is the matrix. What we mean is we are saying this plus this plus this. So that's the meaning of trace. But then you might want to see, okay, these are in component space. What does it mean in the geometric space where I do not have any basis? Like independent of the basis, this is independent of the basis. I can write, I don't have to write this X, Y, Z. In this geometric space, or where I do not use any basis, what is the meaning? So you say that, oh, T11, T22, T33 is nothing but TII. TII in this case
is equal to EI times BI. Agree? And that is nothing but E dotted with B. Notice the final expression is independent of the basis. This is dependent on the all this. Whenever you write components, it is a basis dependent quantity. This is not. Once you understand this, you realize that oh, whenever there are two vectors, I just have to put the dot product in between, and I get the trace out of it. So if it is more than one, so now let's say that is 2. This is also a tensor, correct? There are 2 indices here, 2 indices here, but 2 of them are contracted. So this is a second rank tensor. So how do I take the trace here? I can do the same thing again, and I'll encourage you to do this again. There is nothing wrong in it. But you very quickly realize what is happening is that the outer vector, you take the dot. So the outer vectors is this piece here and this piece here. These two are dotted. Those two are dotted using this dot sign. These two are the independent ones. I just have to take the dot product between them. So the trace here means that this is E, B, dotted with E, B. I just have to take the dot product between E and B. So this is the dot product I'm taking. That means that I can write this as bring it here, so that's B, right? But this you have to do and convince yourself. That's the whole exercise about. Final observation is that oh, this is nothing but the square of this. You do not have to do all these steps, and you realize that oh, this is simply the final vector and the initial vector. You put it together in a cyclic sense, and that is what you get as the trace. But the homework is about realizing that oh, if you do this, for example, here you have to write this as 2 matrices, take the product, get the diagonal element, and you will see that it is exactly the same. But you want to learn that couple of times, and the third time it's okay. Oh, I don't have to do this again. I know what is going on, so I can just take the final 2 pieces and put it together. So that's the idea. Did that help? I don't know how much. Okay, but ask me questions like this. Yeah, anything else I can? Did this help? No. Okay, so could you do the first part of that? All that went well. Okay, so it's only this. So let's try to. So today again, I'm going to be doing dyadic. So all these notations will come again. So maybe it will help. Okay. So and again, tell me if it's Dushmata, how is it? Okay. It's like you could proceed with the homework peacefully. Okay. Yes, no.
Yes,
Yeah, it's a in the classroom. It's not good to ask. Yeah. Sandra, you submitted. I asked you. Nathan, you have any comments on the homework that could help the class? Yeah. Okay, let's proceed, and hopefully all this comes together. That's I can. Do you have the comments, or are you not like you have done this before and probably struggled at some stage somewhere before? Something that you want to add that will help everyone? That
The second one, and this is the next page.
yeah, this one, right? Yeah, that's okay. That's not this one.
That one was easier.
Okay, yeah. Either way, yeah. The observation is that finally you want to put this together. Basis independence has nice features, like especially in quantum mechanics, the basis dependence has some nice features in it. So if you want to keep things independent of that, that has to. Yeah. Okay, so let me proceed and we'll see. Niranjan, you want to add something? That might help.
Not at the moment.
Okay. So homework 2 is due next Friday. We do not meet on Monday. Monday is a holiday and midterm. So one of the reasons why I do this in the beginning is that you see this in some form or the other a lot in electrodynamics. Whatever you're doing, electricity and magnetism, and in your physics 520A, I suppose. And and there are two things mostly involves. Let's start with Gauss's law, for example. Let me review a bit. Gauss's law is the divergence of the electric field is equal to rho, the charge density. It is equal to the charge density at some point R divided by, if you're working in SI units, it is divided by epsilon naught. Okay. So let's say that there is a charge here. There are two charge spheres, and they have different radius. I'm just randomly giving you information. Now tell me, so this is charge plus Q on this. This is the sphere of radius R. Let's say Q1, that's plus Q2. And everywhere else there is nothing else. So there is just two charge spheres. Now take an arbitrary point here. Let's me make it more precise. Like take the center to center, take a point, and let us say this is the line here, and that's your distance y. Now at this point, what is the divergence of electric field? I made this question complicated. A lot of this information is not needed. At this point, what is the divergence of the? This will create an electric field here. At that point, this will also create an electric field. Right? At this point, I'm not asking for the electric field. I'm asking for the divergence of the electric field. How much is that equal to? It's a very straightforward answer. Aryan says 0, and why is that? So notice this, trust the mathematical equation. Divergence of E tells me that there should be a charge density. Anywhere, this is a position dependent equation. At a position, I chose that position. If the charge density is 0, the left hand side has to be 0. That's what mathematics telling me. Right. So I don't have, this was all a distraction of putting different charges. Anywhere there is no charge, right? The divergence has to be 0. In a sense, that's the meaning of the divergence, but usually you have a geometric picture of it. That's your divergence. So if you have a point charge, that means, well, let's say, now I say there is all, instead of all these charges, there is only one point charge. So it's just point charge of radius 0. Okay. And then what is the charge density? Everywhere it is 0, right? Divergence of electric field is 0 everywhere except at one point. So tell me a function which is 0 everywhere, but not 0 at one point. Delta. Right? So Abdullah says delta function, that's not a normal function. If you say it's 0 everywhere, in a sense, when you think of a continuity problem, like functions, you expect that at least at a few points it will be continuous. This is saying it is 0 everywhere, except at one point it is non-zero. So wherever that interesting part is, there is a jump in there. And that's not a pleasant function. That's not a normal function that we deal with. You need some more machinery for that. And that's what we will call a delta function. Okay. Are you familiar with delta functions before? Have you seen like a rough idea of delta function? We've all seen it, right? So we will talk about it more. But those are the two things we want to capture at this point, delta function and the divergence. These two things together we want to do today. If we want to deal with how to address this delta function and the vector equation. So let's come back and do something straightforward. Let's say this is a position vector. Take your basis vector if you want. Let's work in rectangular coordinates. This is x, I hat plus y, j hat plus z, a hat. Notice again, I earlier said this is a basis dependent quantity, right side. Left side is a position vector. That's a fundamental property. I don't need rectangular coordinates to say what is a position vector, right? It's just that the position of a charge is a property independent of the basis. So I can ask, so this is in rectangular coordinates. What is the position vector in spherical coordinates?
Rho.
Rho. Until R. If it is rho, maybe we want to expand on that. Like it's a vector, right? So you want some vector. In spherical, are you all familiar with spherical polar coordinates? Like let's say in rectangular coordinates, this is how it is, right? So that's your vector R, right? And that's your angle theta, that's your Z, and rectangular in rectangular coordinates, that's going to be your phi. Right? That's your x hat, that's your y hat. Okay, is the diagram clear? Maybe. Oops. So in terms of this theta, phi, and r, right? That's the length of this. So x, y, z are the components in the rectangular coordinates, r, theta, phi, and some unit vectors also, right? Remember, you need unit vectors also. And now the question is, what is this in spherical coordinates? No.
Circle is R hat.
R hat, that's good. So this is R hat plus 0 theta hat plus 0 phi hat. Right? R is in the direction of the radial direction. Like I don't need a theta and other things, like that's in the direction of R hat itself. And whatever you were saying was R hat, the definition of R hat, probably you were telling it in terms of the rectangular coordinate. So you're right, but I was asking in spherical coordinates. But notice these are different representation. Just to go one more step, what is it in rectangle? Sorry, cylindrical coordinate. These are the three fundamental coordinates or basic coordinates we use, nothing fundamental about it. But at least those are the most symmetric objects we see around. What is this in cylindrical coordinates? Then cylindrical coordinates is this is your rho, right? This length is rho, that's your z. So it is rho phi z. So then we have to write this in terms of z and phi. It turns out to be, may not be obvious. So this is rho hat plus 0 phi hat plus z times d. That's this triangle here being expanded. So that's a position vector, rho in the rho hat direction, z in the z hat direction. We'll come back and do this more in more detail, but notice what I'm trying to stress here is that this is the same property we are talking about. It's the same position vector. It doesn't need a coordinate system, or this is our handicap that we are used to thinking only in terms of rectangular coordinates. In fact, it made a big difference because the moment coordinate system came, there was a whole scientific revelation sort of waited for this coordinate system. Rectangular coordinates came by Descartes in about 1550s or so. And immediately there was a scientific revolution after that. So this is very, This is our handicap. We like this a lot. We made a huge, significant development after this coordinate system came up, but this is independent of that. And we want to keep that as much as possible, do things in a coordinate independent way. That's what we want, we are trying to do. Okay, so one of the things that comes up is that even though, sorry, not R, this is a tensor, okay, no dot product, no cross product. This is an outer product if you want, but in this course, we have not been putting that circle around. This last time we did, we made this operation, we took this R, and maybe I should say, what is the gradient operator? In rectangular coordinates, it's x hat, d by dx, plus y hat, d by dy, plus z hat, d by dz. Okay. Now, last time we did this in detail and showed that this is actually exactly equal to 1. That means its components are only 1 only when it is 1, 1, x hat, y hat, or z hat here. Otherwise, it's 0. Like these are the diagonal elements. 1 in principle is also equal to, it is good to have what does the 1 mean. And if you have an idea of completeness relation in quantum mechanics, in that sense, if you were to think of this, what this means is that in rectangular coordinates, this means I hat plus j hat plus k hat. Naida asked a question earlier, and I was throwing you the diagonal elements. That was x hat, j hat, y hat. Oh, sorry, k hat, right? The 3 diagonal elements are the components of I hat 1, 1, 2, 2, 3, 3. Right? They all come with 1, 1, 1, and then it's a unit diagram. Okay? So that's a completeness relation. So this has more meaning, but we will need only this much as far as usage goes, but I'm just giving you more information. What will this be in the spherical coordinates? It will be r hat plus theta hat plus phi hat. You may not have a very good visualization of theta hat, phi hat. We will come to that in the next week. We'll start coordinate systems in general. And this one will be rho hat plus phi hat plus z hat. In fact, you can take any coordinate system. It doesn't matter whether it's cylindrical, spherical, or rectangular. Take your favorite coordinate system, and the completeness means that you will need 3 vectors. You need to have 3 vectors, preferably orthogonal, and that's your complete number. Put that in line, and that will always be equal to 1. Again, we will prove this in a very generic way next week when we do coordinate system. Okay. For our purposes, you just need 1. So what you want to take home is the whole of almost all the vector calculus you need in electromagnetism can come from this and one more equation that I read. Notice this is coordinate independent. That's the nice part of this. It doesn't matter which coordinate system you're working in. You can, whatever you derive using this is coordinate independent or basis independent. I shouldn't say coordinate independent. Basis independent. It doesn't matter which basis I'm working with. So that's the nice one. Okay, I'll need one more. I said one more equation to work with all the vector calculus I need. For that, I'll do gradient of R. So this brings back our notation now. Is this a tensor, scalar, or vector? It's a vector. Notice it's not a tensor. There was 2 vectors. Notice there is no vector sign. That's why I keep insisting. If you don't put a vector sign, it's a scalar. In many of your notes, I'm seeing that you're not putting the vector sign. For me, it's a scalar. So I get confused. And presumably, you also get confused. Right? There is no way you can distinguish between R and vector R without, unless you write that. vectors are. Okay, so there is no implicit nature of that. So this is a scalar. This is the magnitude of this vector R. In terms of x, y, z, what is R? In terms of x, y, and z, what is R? Good, very good. So that's x squared plus y squared plus z squared. Right, that's the magnitude of the vector. That's what we mean when we write R. This is in rectangular coordinates. In the spherical coordinates, it's just this R, the magnitude R. And in cylindrical coordinates, it's this square plus this square, rho square plus z square, right? That's this length, rectangle, triangle. This is this length, Pythagoras theorem, plus z square gives you R square. So either way, you can do that. But again, we are trying to not use basis. So this is just the length of the vector, position vector. This is the gradient operator. And we want to see what this is equal to. This is going to be an identity like this. But first time, let's do this. It is not clear what exactly this is. So this is equal to I hat d by dx plus j hat d by dy plus k hat d by dz. And R, let's work in rectangular coordinates. And this is equal to x squared plus y squared plus z squared. Again, it is not necessary to work in rectangular coordinates, but whenever we don't know the answer, often algebra helps. Right? So it gives you trust in whatever you're doing. Okay, this is equal to derivative of x inside this. So this is equal to I hat. There's a 1/2. Take the derivative, it comes in the denominator. This is x squared plus y squared plus z squared. That's 3/2. And take the derivative here, that's 2x. That's just a simple derivative of this quantity with respect to x. Derivative of y and z will be the same because this is symmetric. So that's equal to j hat to y over x squared plus y squared plus z squared plus k hat 2 times z over x squared plus y squared z squared. It seems like it is tedious, but I'm not later on. I'm not going to use this. This is just to convince myself what the answer is. This is just to identify what is on the right side. So this one, 2 cancels out clearly, and what I can denominator is all mistake, right? It's cube. There's also a half. Thank you. Cancel out the half, denominators are common, so that's xi hat plus yj hat plus zk hat divided by denominator is x squared plus y squared plus z squared, that's square root r, that's r cubed. Right? R cubed. A mistake. Isn't it? No. Yeah, what's the mistake? I noticed the mistake. Yeah.
I think it's isn't cube.
Yeah, this is cube, right? No, I'm saying there is a mistake in this. The first derivative, I made a mistake. Yeah, it should be power half, right? So in the numerator, plus half minus 1, minus half. So this is 1/2, right? So my bad. That was not intentional. That was my mistake. So whatever I wrote turned out to be correct. So 1/2. Okay. So this is just R. Okay. And that's equal to vector R divided by the magnitude of the vector R. And that's the definition of a unit vector, right? That's a direction of the position vector. So I have an identity in a sense. It's readable here. Gradient of the position vector, no. Gradient of the length of the position vector is equal to r hat. Again, when I write it in this form, this is independent of which coordinate, even though I worked out in rectangular coordinates, r hat is a geometric property. It's a direction. It doesn't care for whether I'm doing spherical coordinates, cylindrical coordinates, or rectangular coordinates. That's a direction. Same in space, there is a position. That's a direction of that position. Right? This is geometric. No basis dependence in this. These two are geometric properties, basis independent properties, and let's now do more than this. So how do we work on actual vector calculus problems? Let's say in electrodynamics, the first thing you do is divergence of electric field. What is the electric field? You do a point charge. So let's say it's point charge. Tell me something that you know about the point charge in a quantitative way. Let's begin with electric field. What the electric field due to a point charge? Let's say it is at the origin. Make it simple, at origin. Again, these two are the important results. I am going to show that I can do any vector operation using these two identities. Okay, that's what I'm trying to convince. So electric field due to a point charge at the origin is, let's begin with some expression just to have some intuition in our head. What is the electric field due to a point charge at the origin? Straightforward.
Over 4, 5, 7, 9,
Q over R. Is that correct?
by R.
R square, very good, right? So it is R square. So that is 1 over 4 pi epsilon naught. Just a constant, it is innocent, not important. And Q is a charge over R square. Right, good. Something is missing there. R hat, it's a vector, so I need a R hat. Right? There is a potential also. Right, so let's say potential due to the same point charges and Q over R. Vector? No vector because it's a scalar, right? The electric potential is scalar. One of the things we learn is how is these two related? How is the electric field and electric potential related? Multiply by R? Yeah, it's more fundamental than that. It's a gradient, right? That's the same as how is the potential energy U and the force related? Energy and force, how are they related? Energy, no, energy, potential, like energy per unit charge. This is force per unit charge. How are they related? It is always a gradient. If you want to construct a potential energy, it has to be a gradient. Right? Only if it has a potential energy. Not every force has a potential energy associated with it. Okay? Not every force has a potential energy associated with it. For example, friction, you cannot write a potential energy. For that matter, most of the forces you cannot associate a potential energy. There are very few forces that you can associate a potential energy, gravity, electrostatics, magnetostatics, and there are a couple of more strong forces and nuclear forces, but usually it is not easy to get potential energy. So if that is true, then we should be able to show that electric field is equal to negative gradient of energy, but this is potential, right? So is that really correct? So if I take the gradient of that, I should get the electric field. Let's use our machinery here that we are saying we are doing minus gradient of those constants I can remove, right? So that is minus of Q over 4 pi epsilon naught times the gradient of 1 over R. Now, in principle, I can do the same process here. That is what often is done. you go to rectangular coordinates, do the operations and come back. But I say we have already done it. We have done it once. Let's use this. So let's use chain rule. Gradient of something, operate this, and finally you will get acting on the argument is R, right? So for example, if I have to write derivative, right? So let's say d by dx of 1 over f of x would be, what will this be equal to? Help me. This will be minus 1 over f squared times d by dx of f, right? I use the chain rule. I first take the derivative of f, right? That's minus 1 over f squared, and then the derivative of f itself. That's the chain rule that you say, right? Correct. So I want to do the same idea here. Keep this in mind. So this is equal to minus q over 4 pi epsilon naught. Gradient of this, I pretend that this is a function. So this is 1 over r squared with a minus sign. And I use gradient of r, right? Notice the similarity in the steps. Right? Whatever I have, I want to eventually try to use this. I want to get here, either here or there. These are the only two things I'm allowed to use, or I'll remember this. So I'm not done the, I didn't go to any basis notice. No spherical, no cylindrical. I simply did the idea that, oh, there's a chain rule. And this, I know what this is equal to. This is q over 4 pi epsilon naught r hat over r squared. Right? Which is what this is. Is that clear how I proceeded? Like very, like in principle, one step. Right? But I showed that in 2 steps, but it's pretty much one step, okay, or 2 steps if you want. Is that clear how I used that relation? I did not use a coordinate system. Try to appreciate that. And now let's say that's good. Okay, so that seems to be nice. So let's now do one more relation, right? So in electrostatics of point charge, which is sort of the most, if you want to say the most important part of the whole of electrostatics, is that divergence of the electric field, in principle, for any charge, it should be equal to the charge density, right? So rho of r over epsilon naught. Okay, so can we check this? So this we check, right? So this is correct. I started from the left hand side. No, started from the right hand side and got the left hand side, right? Started from here and got mine. Now I'm going to use the electric field here and try to get the right hand side. And right hand side that has that feature that it is 0 everywhere, right? Except at one point. So I should capture that. That will be the hard part, and we will not be able to capture that. So we will have to use something more. Okay, we will start bringing in integral theorems. But let's see how much we can go there. So again, we would like to have a delta function in principle, but I have not introduced delta function. At least it should be 0 everywhere, wherever the point charge is not there. So let's see this. So this is divergence of electric field is equal to, start from there. So that's q over 4 pi epsilon naught. And there is an r hat over r squared. Oh, I need the divergence, right? So divergence goes into the q over 4 pi epsilon naught. Plotted with r hat over r squared. Okay. That's the operation I'm interested in. But notice now the two identities I have, I either know how to operate a gradient on a position vector or on the magnitude of a position vector. at least in this term, I don't know how to act it on R hat as of now. I can derive it, but this doesn't have R hat in it. It's only on the right side. So due to that reason, it is good to not keep R hat to begin with. Write this as vector R over R cubed. That's just being careful. I know. I that's to simplify the problem, like less number of steps. If you do R hat, you won't go wrong. It's just it will be a little longer. You will have to do more steps. Okay. I just changed R by R cubed. Now, if you remember again, just to have an analogy, if you have d by dx of f over g, what is this equal to? I will do first these are functions of x. First, I will do the derivative of f. This is d by dx of f over g. And then I do the derivative with respect to g. So I keep f at this case. That is f over g squared and dg by dx. Correct? So first I took the derivative of f. Like probably all of you guys used it, different ways of doing it. One way is that you hit the numerator, you get f, and keep the g intact. And then you hit the denominator, that's minus 1 over d squared, derivative of g over x. You probably use an identity related to that. However you do it, doesn't matter. So just do it your way. This is what do you say? This is distribution rule for derivatives. That's the same thing. There is a numerator, there is a denominator. It's just that now there is a gradient operator instead of the usual one-dimensional operator. But keep that idea the same. So let me do it here. The two terms, q over 4 pi epsilon naught. This is just something in front. Hit it on the numerator. That's gradient of vector r. Or now it has become divergence, right? Not gradient. It's the moment I put a dot, that divergence, that's over r cubed. That's the first step. Right? And minus of, keep the r intact. Let me so maybe, yeah, let me do this in two steps. It might. So write this as q over 4 pi epsilon naught. This is two functions, right? This is gradient of vector r and 1 over r cubed. And then plus divergent of, this is now gradient of 1 over r cubed. Gradient and then a dot product. With respect to. I was trying to emphasize that to keep this dot. That's why I wrote it in two steps. So it is like saying r over r cubed is like vector r times 1 over r cubed. Then I can use derivative product rule for the derivative. Right? Derivative acts on this, derivative acts on that. So next comes do it explicitly. I'll do this in the next step, keep it intact. I can actually read it off from here, but keep it intact for now. And here, this is r cubed. 1 over r cubed, use the chain rule again, minus 3. So minus 3 over r raised to 4. And then comes gradient of r. Is that clear? Just if you want me to repeat it, tell me, because this is one of the things you want to get again and again. This will come. I'm taking a gradient. There are two pieces in here, r and r cubed. I multiplied that as two functions. R is gradient operating on r, not touching r cubed, touching on r cubed, not touching on r, right? This I kept it intact, operated this because this was very similar to doing this, right? The gradient of 1 over r square was this, so this will be 1 over r raised to 4 here. Okay. This is nothing but r hat. That's an easy part. Right? This was r hat. I told you that we will have two identities. That's r hat. And what is this? The divergence of the position vector. Notice there is no operation in here, right? When there is no operation, this is 1. If I put a dot in between, what does it do? How much? 3. Like this is a trace. Like same problem as you asked. This is the trace, right? The moment I put a dot in between two vectors, that's the trace. So that's a trace of 1, which is 3. So this is 3. So this is equal to q over 4 pi epsilon naught 3 over r cube. This is r hat. We already emphasized on that. R hat times vector r. How much is that? R hat dotted with vector r. How much is that equal to? Like that's the yeah, that's r itself, that's the magnitude r itself. Because this is r hat over r, no, r hat times r, right? That's how we derive it, and r hat dotted with r hat is 1, and it's r. So this is r, cancels 1 over one of the r's, and you get minus 3 over r cubed, which is equal to 0. Which is good because that's exactly what we wanted, right? We sort of expected that this should be equal to 0 everywhere where there is no charge. And for a point charge at the origin, except for the origin, everywhere it is 0. But it did not capture the fact that that point at the origin it was not supposed to be 0. But then at the origin, like if you go back and try to do this more carefully, right at the origin, r is equal to 0. And then we have 1 over a very large or a very large number, 1 over a very small number is very large number, basically an infinity. Minus an infinity, you will say, oh, that's 0, but infinity minus infinity, we're not sure. Right? So we have to be more careful. So we should be careful about this, that r not equal to 0. We are sure about everywhere else, but r equal to 0, we are not sure. Okay. But then, what is it at r equal to 0? That raises the question as to what is the value of the divergence of the electric field at r equal to 0. Okay. For a point charge, what will it be? No, at r equal to 0. Yeah, infinity, right? We expect it to be like, even though for a point chart, I wouldn't expect that answer because naively you would say, oh, that's a point chart. What do you mean by infinity, right? But apparently, whatever this means, the divergence, whatever that means, for a point chart, right on the charge itself, it is infinity. So what does that mean? Apparently, that's what it is. So let's try to do this more, but I've not proved anything. I'm not accepting it, but it's apparently that's what it might be. So it's not very clear what this is. So let's do some more work for this. Right? So yeah, so now this finishes this using vectors. Now we are in the delta function part. Okay. So to get the delta function part. So now let's take divergence of electric field. Okay. And like which is basically 0, right? Everywhere. And let me say I now have so this is my point charge. Right, that's at the origin. And let me now integrate this everywhere on a sphere of radius r. It has nothing, that radius r has no meaning. maybe I shouldn't put the R at all, just to have. And usually R is associated with some radius or something. So let's say this is epsilon of epsilon. Some arbitrary volume I pick, which is enclosing the charge. This value here, right, gradient, is equal to 0 everywhere inside of that sphere. Right? Except at that point, which I don't know. I said everywhere other than that point, it is 0. At that point, I'm not sure. So I want to add them everywhere in that volume V, right? That's the volume V. If I add a lot of zeros, how much do I get? 0 plus 0 plus 0? 0. I should get a 0, right? So I should get, expectation is that I should get a 0 everywhere, except that tiny piece. Okay? But then I argue that suppose I were to do an integral, let's say yeah, let's take an integral of the function, right? And let us say that that's your epsilon. And this is my function f of x. Integral of dx f of x. Okay. So integral of a function is the area under that curve. And I go from point A to point B. A to point B such that B minus A is epsilon. Is that clear what I'm doing? I'm giving an analogy for this. This is a lot of sum. So I'm summing. So I'm going from a one-dimensional problem A to B of this function. That means it's the area under that curve. And then let us say that I take the limit epsilon tends to 0. Or let me change something. Okay. Change the form. Okay, sorry. So there is A here, there is B here, and there is a point here, which is right. Usually you would present it like that. So that's your point 0, let's say. And this could be minus A, that's plus A. I have a function which is 0 everywhere, then right somewhere in between, it goes up, comes back, and goes in here. And I don't know what the function is right at that point. I know the function everywhere else except that point. Okay? And I also say that suppose it was really 0, then it is minus A to plus A can be written as minus A to epsilon naught dx f of x and plus epsilon minus epsilon to plus epsilon d of x f of x plus epsilon to a d of x f of x. If the function is 0 everywhere, this will be 0, that will be 0, and usually what this is the area of this piece right underneath in here. That's what I was trying to do that earlier. In the limit epsilon tends to 0, what is that area equal to? So again, we have this as minus epsilon plus epsilon, and the function is like this. In fact, I don't know what this function is, but whatever that function is, in the limit epsilon tends to 0, what is the area of a rectangle? 1. Which is going epsilon 0, which has no width. Area of a rectangle which has no width, which will be 0, unless this becomes infinity. At 0 times infinity, I don't know, especially for example, if this was 1 over epsilon naught. Right? If I multiply this by epsilon, that they cancel out and it can give you 1. I think that's what probably Abdullah you're forcing what we are expected, but unless I tell you that this is zero, always zero. So basically, what it means is that in an integration, I can take out a point and still the integration remains the same. Integration is a region dependent quantity. For a point, it is zero. You can remove a point from the integration and still it will be zero. That's like saying this. So I have removed a zero. That's what we are talking about here. We are taking an integration and there is only one point there. So I can remove that point and it should be fine unless it's an infinite. But nevertheless, let's do this irrespective of whatever the geometric interpretation we have. Let's do this, but we know what is called a divergence theorem. What is a divergence theorem? Volume to surface, or in one dimensions, like this is the analogy, poor man's divergence theorem. Partial derivative of x with respect to the function a to b, this is equal to like derivative and integration are anti to each other. So this is nothing but f of b minus f of a. This is in a sense what Newton discovered, right? That like derivative ideas were there, integration ideas were there before Newton came in, but he saw the connection between the two. So this is sort of so the fundamental theorem of calculus, if you want. But the idea is that if you have a function f of x, right, the volume is you go from a to b, right? Or volume is integration is about going from a to b everywhere. But if the integrand is a total derivative, it cares only on the boundary. And a boundary of a line is just 2 points. Right? F of b minus f of a. Here we have a volume. This is a gradient, a more generalized version of a derivative. It's a poor man's divergence theorem here. And the volume is enclosed by a surface. Right? What's the boundary of a volume? It's a surface. So instead of having 2 points, we have the whole surface. Right? So this will be equal to the surface. It's a vector quantity. Surface area. Area is a vector property. Vector is area is not a scalar. We say it's length times breadth. It has a direction also. It is a cross product. Right? So without worrying about that, it is dA dotted with the electric field. And this is a closed integral in the sense the surface has to close the integral. And this means the surface enclosing the volume V. Like there are lots of closed surfaces. Here I'm talking about a specific surface, the surface that encloses or the boundary of the volume V. Okay. What is that equal to? Now I can do this immediately because as far as I know electric field on the boundary, the good point is that I escaped that zero. Now I'm on the boundary. There was this problem that at the center, we were suspecting a infinity, like of the divergence of E. So calculation would be very difficult whenever there is an infinity. But using this theorem, I have gone out of the infinity. I am now on the surface. Surface is perfectly okay. We don't see any problem on the surface. So I can do this calculation. Earlier I couldn't. Like here I cannot because there is an infinity there. Or at least I suspect there is an infinity. So let's do this. So that's equal to this is do this as a the unit vector is r hat dotted with electric field also has an r hat and it is 1 over r squared and 1 over 4 pi epsilon naught. Notice again geometric. I'm not using any properties except the geometric properties. I'm not using a coordinate system anywhere. This is the geometric property. This is r hat times r hat, that's 1. And area itself, if I am on a sphere, this is integrated over the d theta and d phi, which is the angle, right? Solid angle. The omega here is equal to d theta, d phi, and sine theta. That's a solid angle associated with a sphere. We'll come back to that in more detail later. If you must have seen it somewhere or the other in this form, but if you don't have a picturization of that, you can come back later. E omega, and then there is r square, right? That's the area is the solid angle times r square, and that is a 1 over r square. Nicely balances out. R square cancels out. Very crucial, because otherwise this balance will not work. And that's equal to, oh, there's a q also, right? And we say this is solid angle again if you want to close. And if you add up all the solid angles, all the infinitely tiny solid angles on a sphere, how much do you get? It is 4 pi. Like on a circle, if you were to do, that is 2 pi. On a sphere, it is 4 pi. Quiz, sorry. Quiz. There was no quiz today? Apparently no. Okay. So pictorially show me this. Pictorially use a diagram to show this and prove that this is equal to 4 pi. Show that this is equal to 4 pi. So 2 parts to this quiz. First do this and you get 4 pi. So that's equal to q over epsilon naught. If we were to recap whatever we did, we showed that del divergence of electric field for a point charge is equal to 0 everywhere, and we suspect that maybe at r not equal to 0, it could be funny, it could be infinity, but it's 0 everywhere other than r equal to 0. And we are saying that you integrate it over a sphere, that's not 0. Okay. So we have a function that is 0 everywhere except at the center. But when you add all those zeros, it gives you q over epsilon naught. How is that possible? Okay, so that's a logical problem now, right? Give me a function, like remember this is a charge density, right? Del dot E should be the charge density. So charge density of a point charge, it is 0 everywhere. At that point, it cannot be normal number because then it will be 0. So it must be an infinity. So we introduce a delta function for this. So last 2 minutes. And you have in your homework, you work with delta functions, at least as a proof, right? But let's think of a function f of x in the following way. F of x is equal to 0. Let's say, 0, 1 over a if x is less than a or greater than 0, and it's equal to 0 otherwise. Okay. So how does this look like? So that's 0. That is A. And it is 0 everywhere, so that's here 0. And then it becomes 1/8 here. So it is a constant 1/8. So the height of this is 1/8, and again it goes to 0. So this is actually not to be shown. The function jumps. There's 0 everywhere. It comes 1/8, and then comes down and it is 0. Okay. Is that clear? Okay, so I now want to do integral of dx of f of x is equal to, and let's go from minus infinity plus infinity, so everywhere, right? So usually the integral is the area under the curve. So area under the curve, it is 0 here, 0 there, and this is equal to, so that's area. And what is that equal to? Area of this tiny box. 1. Right, it's 1 because it is A. That's 1/8, so that's A times length times height. So that's 1. So that seems to be obvious. But now, what if I were to take the limit of A tends to 0? I think of the situation where f of x is equal to 1/8 and 0. And this is again 0x less than A otherwise. But now if you take the limit, A tends to 0. And you suddenly notice that this answer will be independent. Now, what this has happened here is that in the diagram, this is pretty much, this is going to 0 here. This is very tiny, but 1/A is 1/0, so that shoots up. Right? So, and that's an example of a delta function. That's not a very convenient piece, but always under the integration, it's well defined. So notice this is a well-defined concept. Whenever you write it in this way and you take the limit, there might be challenges. If you want to do this, you want to be more careful. It's not that it is wrong, it's just that you want to be very careful when you're working in this here. But inside the integral, delta function is very much okay. That's always 1. Okay, it will come out to be the simplest integral, that whenever there is a delta function, it's equal to 1, or the value of the function is taken there. So our delta function would be, so delta function will be minus infinity to plus infinity dx. So f of x now, I'll call it delta of x. That's equal to 1. That will be the property of a delta function. Always we will use this feature, integral of a delta function. Often this will come with a function delta of x, then f of x. I'll take one more minute. What is that equal to? This is equal to 1, and this is equal to 0 everywhere. This is equal to 0 everywhere except when x equal to 0. What else can it give? It is f of 0. This will be your favorite integral from now onwards. Whenever there is a delta function, it's the most immediate answer. You just take the function and replace it with that. Next, generalize this a little bit more. X, if the delta function is not at x equal to 0, instead if it is at f equal to x equal to a, then this is f of a. And I'll stop here. In your homework, I don't ask you to evaluate this delta function. That's what we will do actually in a lot of problems. In your homework, you will be actually constructing delta functions. When I say point charge is a delta function, what is the charge density for a disk? So it's a little thought you have to give into it, but it's a good exercise. And you will use it in ENTs. I'll stop here. Thank you. Oh, Niranjan,
Hey, Dr. Sajas.
you know all this.
I have seen this. Today it was fine, but last week I feel like I haven't seen a lot of things with Dyadic and stuff.
Got it. Yeah.
So I really like it.
Okay, good.
Okay. Thank you,
Thanks.
Dr. Sajas. Then we don't have class on Monday, right?
Oh, no, we don't have class this, it's holiday, right? Yeah, so
Got it. All right then.
ask me to give a class. Yeah, let's have some holidays.
Okay. See you then later.
Bye, Niranjan.
Bye.
Thank you.